So, good afternoon, everyone. Thank you very much for attending this webinar. The topic of this presentation is recent advances in measuring volume change of unsaturated soil specimen during triaxial testing. So, this work is being done by my PhD students Xiong and Sarah Fiak. Okay. So this is the outline of my presentation. First, I will give a brief introduction regarding the background of the research, and then we will talk about the limitation of the existing methods for measuring volume change of soil specimen during triaxial testing. The focus will be on introducing the principle of photogrammetry-based method we developed in our group, and then also the post-processing and some validation tests. Finally, some conclusions will be made. Okay, so normally, if we want to design for foundation, we need test the soil to get its volume change and the shear strength. So as a result, volume change is indispensable component in the triaxial testing. So normally for saturated soils, this is simple because we only have two phases in saturated soils. We have soil solids and water. As a result, the amount of water, the volume change of the soil specimen is equal to the amount of water flow in or flow out of the soil specimen. By measuring the amount of water flow in or flow out of the system, we can measure the volume change of a soil specimen. And if we want to do undrained test, normally there is no volume change, and then the we can measure the port pressure, which is positive. But not majority of our infrastructure actually is built on unsaturated soils. For unsaturated soils, there are three phases. One is the soil solids, water, and air. And when you apply load to the soil, there is volume change, but there might be no water coming out of the soil. So the volume change of the soil specimen not equal to the uh, amount of water flow in or flow out of the soil. And most importantly, port pressure is negative. So it, it poses a great challenge for researchers to investigate the behavior for unsaturated soils. So in 1959, Bishop and his co-worker developed a method to do triaxial tests for unsaturated soil. The major modification is to add a inlet cell into the existing triaxial testing system. So the idea is very simple. So for saturated soils, because for unsaturated soils, because we cannot measure the amount of water flow in or flow out of the soil specimen, and we cannot measure the volume change of the soil. So maybe we can. An idea is maybe we can merge the amount of water between the soil and the aquinic cell, so that we can measure amount of water flow in or flow out of the cell to get the volume change for unsaturated soils. The idea is simple and straightforward, but it's not working. The reason for this is when we do triaxial testing for unsaturated soils, normally we need to apply load, confining pressure to the soil specimen. The confining pressure is also applied to the aquatic cell, which can make the aquatic cell to deform naturally. As a result, the volume change of the water here is not equal to the volume change of unsaturated soil specimen. So in 1959, Bishop and his co-workers, they made some modification for that. What they did was they used a double cell system. So we apply confining the port pressure in both cells with the same kind of confining pressure. As a result, you can still apply the confining pressure to the soil, and the confining pressure water pressure is applied on both sides of the inner cell. Because the pore pressure is the same, so there's no deformation. As a result, we can measure the amount of water flow in or flow out of the system and use it as a volume change for unsaturated soils. Um, Another modification they did was to replace the process stone with high air entry disk. The characteristic of the high air entry disk is when it is saturated with water, only water can flow through the soil, the disk, and air cannot go through the disk. And then another modification is on the top. They they add a L channel to supply high air pressure. The high air pressure will be applied to the water inside the soil and squeeze the water out of the soil. So by controlling the pore air pressure and the pore water pressure difference, we can control the suction. In this way, we can measure the volume change for unsaturated soil. In the meantime, we control the suction. So the method is straightforward and it's suitable for large streams, and it is extensively used. But the problem is it only eliminate the deformation along the natural direction, right? So actually the pore water pressure is also applied on the top and the bottom. As a result, there is also deformation which can influence the accuracy of the measurements. So there's another version of the double wall system, which is a differential pressure transducer. As you can see, actually the inner cell is much smaller, and the top is completely submerged in the water. Another thing is they used a differential pressure transducer to measure the water level in amount of water flow in or flow out the inner cell to use it as volume change of unsaturated soils. The idea is the same. So we classify it as a double cell system. The limitation of the double wall system is it requires major equipment modification. Normally, it takes about 80,000 to 100,000 US dollars to modify the equipment into a double wall system. And sometimes the top and the base, there is a deformation and we cannot consider it, right? So the L bubble, there could be L bubble inside the cell or inside the channel, which are difficult to remove. And when we use acrylic cell, it can absorb water, and the water absorption is affected by temperature, pressure, and the time. For unsaturated soil, normally it takes 1 to 3 months to finish one test. As a result, the impact will be significant. Another thing is the acrylic cell can creep under pressure, which makes the calibration process very difficult. You can use a steel inner cell, but you cannot see the soil specimen anymore. You cannot see if there's an air bubble inside or not. So yeah, these are the limitations of the double wall system. Also, it has so many limitations. It is still the most. It is still the most frequently used testing method for unsaturated soils, and this is considered as the standard for unsaturated soil triaxial testing. Some other researchers also proposed to use two air pressure and water pressure volume controller to measure the volume of air and volume of water separately during the triaxial testing for unsaturated soils. The limitation is it requires an additional L volume controller, which is roughly about the dollar each, and it has the assumption that the L phase must be continuous. And because we are measuring the L phase volume, and the L phase is very sensitive to temperature and atmospheric pressure changes, which is difficult to control. And if there's L leakage, or if there's air diffused through the tubes connections and high air entry desks, it will be very difficult to detect. Due to all these limitations, this method has not been extensively used. I think there's just one or two publications regarding this method, and then that's it. So another method might be to use special design miniature LVDT to merge the lateral strain and then use conventional LVDT to merge the displacement in a vertical direction. Okay, so for example, this is a special designed LVDT which costs about $2,000. Okay, so it requires specially designed waterproof LVDTs. As you can see from the previous slide, at most, you can put three LVDTs on the soil specimen due to the limited space. And it's not suitable for soft soil specimen because, yeah, the LVDT, during the installation process, it can deform the soil specimen. And it will not be accurate when there's a shear plane. Actually, for most of the soil, when the soil fills, there's a shear plane. And the error was raised due to setting, closing of the gap and alignment, because you want the LVDT to be installed perfectly horizontal in a horizontal direction. And then another method is to use some kinds of optical laser scalar method. So what this is, I take from the report from some researchers at the Technical University of Catalonia in Spain, Barcelona, Spain. So what they did is they replaced the outside cell with very thick stainless steel. And then they open two windows, and then you use a laser to scan both sides of the soil specimen. In this way, you can get the profile of the soil specimen along the two opposite sides. In this way, we can get the lateral strain. You can also merge the vertical strain. From there, you can get the volume change. So again, it requires significant equipment modification, and the localized display. You can only measure the localized displacement along the two opposite sides only. Another very important limitation for this one is the refraction was not considered. So yeah, as we know, when light travels through two different kinds of optical media, it can cause light to bend, right? This is called the refraction, which is in our high school physics. So I asked my student to half fill the triaxial cell with water, as you can see, with or without water, due to the effect of the refraction, the soil the soil specimen has been distorted significantly. So if you do not consider refraction effect, your measurements cannot be accurate. So some other researchers also use the X-ray computed tomography to measure the volume change of unsaturated soils. So it is equivalent to actually performing a lot of X-ray examination on soil specimen. So the benefit of this method is it can see the inside of the soil specimen, okay? And then you can make a lot of scans, and then you can stack them together to get the 3D deformation of the soil specimen. But many of you have go to the hospital and done X-ray test, right? You know how careful the doctors are, right? So the limitation of the X-ray CT is it will be much more expensive. To have a system like this, you need at least several $1 million, right? And you need a special design room for that. In the United States, only 2 universities this kind of system, and one was broken. Last time one was checking with Washington State University. Okay, I hope you already fixed it. And another thing is it has potential health concerns due to the X-ray, use of X-ray. And it requires special design. The triaxial testing system requires, the requirement is need no metal involved because metal can change the image for the X-ray, absorb the X-ray, right? And then because for unsaturated soils, it takes a very long time to run a test for unsaturated soils. As a result, it will be very, very expensive to run a test for unsaturated soil for routine engineering purpose. So with the advances in the digital cameras, some researchers also use the digital image coordination to match the volume change for unsaturated soils. So the idea is you can take 2 pictures for the soil specimen at the same location at a different moment. So the soil specimen actually has a texture. By doing some kind of statistical analysis for the texture, you can guess, oh, this patch, after you apply a load, has 99% of the similarity with the initial patch here, right? Of course, you scan the whole picture and then do a image correlation and find out, oh, this patch originally is here, this patch is originally here. If you know the relative position, then you can actually calculate the string in the soil specimen. And the limitation for the digital image correlation is it did not consider the refraction, so it can only test the soil if you run the test in the air. And you need accurately determine the camera position, especially you would like to get a partial 3D construction. And because the soil blocks the view of itself, you cannot get the total volume change. You can only get a partial of the 3D construction. So some other researchers also thinking about to correct the reflection by using digital image analysis. So the idea is to put a camera at a known position relative to the acrylic cell. And then by knowing the position of the camera and the location of the acrylic cell and the specimen, actually you can do some kind of retracing to correct the image. For example, these are the image taken by a camera. You can detect the edge, and then you know its location in the image. And then with knowing the location of the camera and the soil specimen, you can actually make some correction to correct the natural profiles. So this is some researches even extended for the 3-dimensional cases. So this is the partial 3D digital analysis results, which was done by University of Tennessee at Knoxville. So the limitation for this method is it has a lot of assumptions. For example, the soil specimen and the acrylic cell has to be perfectly cylindrical and installed vertically. The camera has to be placed perfectly at the horizontal direction. Shooting direction has to be exactly passing the center of the chamber. soil specimen has to be installed exactly at the center of the chamber. Camera, chamber, and the soil specimen are accurately known, and the deformation of the actinic cell is negligible, which is not possible, right? And the soil specimen and deformation occurs homogeneously along the radial direction. So all these assumptions are very difficult, if not impossible, to achieve. As a result, the method will not be very accurate. So this slide summarizes the existing methods to measure the volume change for soil specimen during triaxial testing. So here we would like to introduce a method developed by my research group at Missouri University of Science and Technology. So the method is very simple. You can use the conventional triaxial testing system for saturated soil to do research for unsaturated soils. What you need to do is just print some specially designed coded target necklace at a different location of the actinic cell. For example, here we use it to do the coordinate system. We put it on a rod, we put something on the actinic cell, and we have two rows on the actinic cell. And for the soil specimen, we print the coded text on the membrane. So you just do the test according to the conventional way. And then what you need to do is you just need a commercially available digital camera. You can perform the test according to your design, and then you just walk around the whole testing system. You can take pictures from any upstream location, from any shooting direction. And then as long as you can see the soil specimen, you are doing the measurements for the soil specimen. So for each picture, you are doing many measurements for many points. And you can take many pictures for the same points. And then after that, you give the pictures to us, and then we have a program which can be used to analyze the pictures to reconstruct the 3D model of the testing system from which we can get the soil specimen. We can not only get the location of the point on the surface, we can also back calculate the top and the bottom plane of the planes of the top cap and the bottom cap. And then we have an enclosed system. We can do the mesh generation. We can get the volume change for soil specimens. And we can not only do the total volume change, we can also do like localized string calculation. So it is equivalent. This method is equivalent to install a lot of non-contact LVDTs on the soil specimens. So for every point here, it's equivalent you install to installing LVDT on the soil specimen. So this is the membrane we use for the test. So yeah, each point is specially designed, and our computer program can automatically recognize the points. Okay, so the procedure is this, very simple, as I talked about previously. You just need to post some the coded targets on the acrylic cell, and use the membrane with coded targets printed on it. And then you can take pictures around the acrylic cell with the soil specimen inside. And then the rest is the computer program, which can help you to do that analysis. So the idea of actually the principle of this approach is very simple. It is based upon the photogrammetry. Okay, so for example, yeah, this is the Triaxial testing system, and the blue points represent the location we take a picture. For example, at this location, if we take a picture for the triaxial testing system, we have a picture like this. And then for the same kind of triaxial testing, if we take a picture at this location, this is the picture you are going to get, right? So for the same point, for example, this point with the ID of 187, on the two pictures, if you merge its coordinates relative to the up left corner, you can merge its coordinates. You can find that its pixel coordinates is this one and this one. The difference, if you look at here, in the horizontal direction, the difference is 35, and in vertical direction, the difference is 20. So there's a small difference in the pixel numbers, right? So this small difference is mainly due to when you take a picture, you have different shooting location and shooting directions. So by using this small difference, we can set up some equations which can back calculate the camera position to accuracy to 2 to 3 microns. Once you know the camera position and the picture, you can reconstruct the 3D model of the soil specimen. So this idea is very simple. It's called the photogrammetry. So how many points do you actually need to back calculate the camera position? The answer is 6. The reason for this is I can set up my coordinate system to the center of the first camera location, and then the second camera position in the coordinate of the first camera position. It has 6 unknowns. It has X, Y, Z coordinates and 3 shooting directions, right? So you need 6 points to set up 6 equations to solve this camera position relative to this camera, right? And we also need a scale. So if we can specify the distance between any 2 points, then we can reduce the requirement to 5 points. So with 5 points, you can back calculate the camera position, and then you can reconstruct the 3D model for the whole system, right? Remember, for a typical iPhone, your pixel number is 16 megapixel, right? So you have a lot of points which can help you to set up the equation. This is the reason why the 3D reconstruction is so accurate, because we have a lot of redundancy, which we use for the statistical analysis to best guess where is the camera position, okay? So the idea for the photogrammetry is very simple. So you have studied in high school for a pinhole camera model, right? So you can have a box, you can have a small hole there. Yeah, you can generate a picture of the tree inside that box, right? The reason for this is the light is transferring us along a straight line. So this is a high school physics. So the photochrometry is the same. The lenses inside on the camera is equivalent to the pinhole, and the image sensor is equivalent to the back screen, which you generate your image. As you can say, as you know from a high school physics, it will generate an upside down image from the pinhole camera, right? So this is not convenient. So in photogrammetry analysis, normally we find a symmetrical plane, which is a symmetric plane of the back screen to use it as an image plane, right? So it has the same distance, which is the focus length to the center of the camera of the pinhole. And then if you have an image object point, it can generate an image point on the image plane here. And then for the image sensor, you have its physical size. And then you can measure the corresponding X and Y values relative to the up left corner And if you have a pixel number along the X and Y direction, actually you can change the pixel number, which you measured here, into the physical size of the X and the Y. And then you can, because the focal length is known for your camera, so you can change the two-dimensional points into a three-dimensional local coordinate system like this, right? And then by using the same camera, if you are taking an image for the same kind of point, you can also set another coordinate system. All this coordinate system can be transferred into a global coordinate system so that you can set up an equation to do the calculation. So yeah, the equation to do the coordinate transformation is something like this. You have the three rotation angle. This is the rotation matrix, and then this is the translation matrix vector, right? So in this way, you can transfer any of this point into the 3D coordinate system. And then you can set up an equation. So what it says is the object point and the image point in the first camera and the center of the first camera, this is a straight line. The same thing is for the second image point and the second camera. This is a straight line. And if you connect the center of the two camera positions, you have a triangle, right? So in your advanced, actually it's the linear algebra, you can set up an equation to say, oh, if these three lines are on the same plane, they have to satisfy this equation, right? So this is how you get your first equation. Of course, you can find another 5 to 6 points. Then you can solve the camera position relative your global coordinate system. So it's fairly easy. The principle of the flow geometry is very easy, and it has been well established for at least 150 years. So yeah, by using the photogrammetry, we can actually back calculate the camera position and find out the location of the acrylic cell. Remember, the acrylic cell will deform under the applied pressure, so we need an equation to describe it. So we can say that the acrylic cell initially has a shape of cylindrical shape. So the cylindrical shape has an equation like this, right? And then when it deforms, it will deform into a drum. It will be the equation like this, right? And after that, this is the equation for the drum shape of the acrylic cell in a standard coordinate system with the orange in the center of the acrylic cell, right? But normally, the acrylic cell is in an arbitrary coordinate system we use to back calculate the camera position. As a result, we need to do some kind of coordinate transformation. If we transform into an arbitrary coordinate system, then this is the equation you will get, right? So this part, actually, this part is not that difficult. It can be done by a lot of software. The most difficult part is to handle the effect of refraction. So we already started in high school. The Slaughter's law is a theoretical equation to describe the refraction of light, right? So you must be very familiar with this equation, which says the refracting index of the first optical media over the refractive index of the second media is equal to the sine of the theta 2 over the sine of the theta 1 here, right? So you are very familiar with that. So for us, because we are doing the measurements for 3D objects, so we need to rewrite the equation into the 3D formulation. This is the 3D formulation of the Snell's law. Okay, so how to do the refraction correction? So this is the idea. So by using a photogrammetry analysis, we use the point, which is posted on the acrylic cell outside. We can back calculate the camera position and the acrylic cell location. And we also use the equation to describe the acrylic cell. In this way, you know your camera position and you know a point on the image, right? So by connecting the camera location and the image point, you can find the incident rate of the point, right? And then you know the acrylic cell location. So by making these two equations, straight line and the acrylic cell equation equal, you can find actually two interceptor points. The first interceptor point is what you want. Well, you have a refraction, right? So yeah, you can find the location point D, find is normal because you know the equation. So this is just advanced mathematics, right? And then you can find out what is the outgoing ring, because you know the coefficient of refraction index for the acrylic cell, right? So as a result, you know the point, you know the direction of the outgoing ray. So you can do a second calculation because for the inner cell, it has the same shape as the outside cell, right? So, so we can use the same equation to describe the inner cell. The only difference is we need a minus a uniform thickness, right? In this way, we can use this ray to intersect with the intercell. We can find the inner cell point and the outgoing ray again. So this is the location where the light comes from to generate this image points on this at this image location, right? So yeah, I can do the retracing for the same point from different camera positions. And supposedly, if everything is working perfectly, this 3 line should intercept to the same point, and we can find this point, solve this point, we can get the 3D coordinates of this point. So we can reconstruct the 3D model of the soil specimen. But in reality, there is always small errors during the measurements. As a result, these 3 lines might be 3 lines in a space which do not intercept. So what we do is we assume there is a point which has the shortest distance to all these 3 rays. And then this is the point we would like to find. Because yeah, even though there's small arrows, this represents the 3 measurements of the same point. It should be roughly at the location of the real points there, right? So what we needed to do is to just use a least square optimization to find the point, which has the shortest overall shortest distance to the multiple rays to get the points, right? So this is a 3D dimensional representation of how the method works. Yeah, this is the equation for the least square optimization to find out the 3D coordinates for the points on the soil specimen. So this is the idea. Of course, we also need, after we get a lot of points, we have to reconstruct the 3D model of the soil specimen. We need to do a lot of post-processing. So we can get an absolute volume tilting extraction and localize the string. So for example, in the past, normally if we do the conventional, do the testing in conventional way, we measure the soil specimen in the air, and then we put the membrane on, we assemble it, fill it with water, use carbon dioxide to saturate the soil, we flush the soil with water, we add water to get the carbon dioxide out, and then we apply back pressure to check if the soil is saturated, and then we can run some tests, and we assume the volume at this point is the same as this point, right? This is what we normally do, but during this whole process, the volume of the soil might have changed, right? As a result, your test results might not be accurate. Of course, you might say, "Oh, I don't really care because I want to care about the changes," but this is not the case. For example, the three dotted line has the same kind of slope with the three solid lines, but they actually represent a different soil behaviors, right? So you do care the absolute volume of the soil during testing. So what we developed was by an analyst PhD student named Sarah Fiat. So to develop a method to calculate the absolute volume of the soil. So the advantage of this photography method is it can do measurements for any point which is visible, but it cannot do the measurements which is hiding. For example, in order to calculate the volume of the soil specimen, we have to know where is the location of the top plane of the cap and the bottom or cap plane of the pedestal, right? But they are not visible. But so it cannot be measured by our method. So the method developed by Dr. Fiak was, if you think about it, if we have some points which is on the top cap and the bottom pedestal, which is visible, then this point has a fixed distance to the top plane and the bottom plane. So by using this kind of fixed distance, if we know the 3D coordinates of the points on the top cap, we can back calculate the plane, top plane. In this way, we can find under the bottom plane. In this way, we can actually find out the actual 3D model of the soil specimen, and we can generate a 3D mesh. We can also interpolate it to get more points on the surface. And then we can get the volume change of the soil. Because of this, because we know the top plane and the bottom plane, we can also find the center of the top and the bottom plane, and we can also find the normal of the top and the bottom plane. So by comparing the two normals, we can find the tilting angle of the soil specimen when you do the testing. And then by projecting the top center to the normal of the bottom plane, we can find the eccentricity to say if you apply load exactly past the center of the soil specimen, right? So this is the idea. Yeah, this is how the possible combinations of different kinds of tilting and eccentricity. So conventionally, we will always assume we have a perfect cylindrical soil shape. And then we will always put the soil in a vertical direction, and the top cap is perfectly put it at the center of the soil specimen, and is perfectly to the vertical direction. The node is perfectly in the vertical direction. In reality, this might not be true. It has all kinds of possibility to go wrong, right? But at present, there is no method to actually tell us if you do a test correct or not. So with our method, actually we can measure the tilting and the eccentricity. Besides this, we can also do the string localization because we have so many points. We can calculate the localized string by compare the soil specimen, compare these points at the different moments when you apply load. So we also did a lot of validation tests. Due to the limited time, I will go faster. So we used the certified gauge blocks and the digital caliper to do the calibration. We reconstruct the 3D model of the digital of the certified gauge blocks in the air, and we use different kinds of block, which we know the exact length of the block. For example, it's 1 inch, 2 inch, 3 inch, 4 inch, right? And then when we put a different block into here, we know exactly what's the distance of the points moves. And then we use photogrammetry to reconstruct the 3D model and calculate the distance. So we can find the average absolute error is about 2.3 micron. And the average error is just 1 micron. So this is very high accuracy, which represents the accuracy of the photogrammetry in air. And we also validate the measurement of the proposed method for the points in the water. So what we did was we used a rigid stainless steel cylinder to use it as a soil specimen. We put it into the cell, and then we ran tests, right? We fill it with water, and then we run tests at different kinds of confining pressure. When we apply the confining pressure, actually the cell can deform, and we can do the 3D analysis. For example, these are the 2 pictures we taken from the test. This slide shows the deformation of the acrylic cell under different kinds of confining pressure. So as you can see, when we fill it with water, when we did not apply cell pressure, it is not perfectly cylindrical, right? It's not a straight line. The reason for this is we use the old cell, and there's already some kinds of plastic deformation because the previous use. And then with time, it can deform, right? So we can do the 3D retracing after we know the camera position. For example, for 1 point, we have 7 pictures to do the analysis. If you look at it here, there's no difference. When you enlarge it many times, you can say, oh, there's some differences, right? So we evaluate the accuracy of each point by comparing it with the measurements in the air. What we found is that maximum difference is 0.076 millimeter, right? 75 micron. On average, it's just about 65 micron. So it's highly accurate. So we also do the total volume measurement and string localization. So for example, for this one, we use a lot of points, and then we use saturated soil to validate the results. Then we took a lot of pictures. As you can see, we took about 36 pictures. We can reconstruct the 3D model of the soil specimen. And then we can find the top and the bottom. And then we can cut the soil specimen. And then we can find the eccentricity and the tilting angle. So as you can see, conventionally, we do the measurements when the soil is in the air, and then assume there's no change during the installation process. Once we start the test, and then we measure the amount of water flowing or flow out of the soil to get the volume measurements, right? Relative to the initial point. But the problem is if the initial measurements is wrong, the rest, all the data is wrong, right? So this is the measurements we measured by the photogrammetry method. As you can see, at the very beginning, if you use the digital caliper, you already have some mistake, right? And then during the installation process, when you put it in the triaxial cell, you are disturbing the soil specimen. When you inject the carbon dioxide, the soil is swelling. And then if you flush it with the air water, there is a compression because you are applying seepage force to it, right? When you apply back pressure, there is swelling. And then when you evaluate the situation, you apply back pressure, it compresses the soil a little bit. And then when you do the loading, you start to change, right? As you can see, you have significant difference during the installation process. If you do not pay attention to it, your result will completely make nonsense, right? But once after that, actually our results match the relative moments for the auto displacement method actually very well. And then you can also find out the soil specimen actually is not installed very well, right? So the red line represents the tilting angle is keep increasing during the process. If you have a slight tilting angle, with time when the soil deforms, it will increase. And then also you have the eccentricity, right? The change. So this is something which has never been able to be merged in the past. Of course, we have the full field displacement and the localized stream measurements, right? So yeah, we can also find the development of the shear band. With time, you have stress uh, localization, right? So this is what we have done. Actually, another PhD of my student, Xiong already developed an advanced version. For the previous one, you just need one camera, but you can only do a test for when the soil specimen, do a static test. When the deformation of the soil specimen is not very rapidly. So every time when you need to take pictures, you need to pose the test and then walk around and take pictures for the soil specimen. But there are many cases, the deformation of the soil specimen is continuous. For example, the soil can creep under constant load, or if you have a dynamic loading, you need measure the volume change of the soil specimen continuous. So my PhD, Xiong has developed a multiple camera system in which he used a very low cost surveillance camera. Each of them is just about 100 to 150 US dollars. And then he put a lot of camera surrounding the soil specimen by taking the videos of the whole testing system. He can actually back calculate the camera positions and then reconstruct the 3D model. He make the code high efficient. Actually, for each analysis now, it just take about 2 seconds. And then for every second, for this kind of camera, you can do 15 measurements. The whole system is just about $2,000 to $3,000. So we will have some publication very soon, and please stay tuned. So this is the conclusion for this presentation. We developed an optical method which integrated a photogrammetry, multiple retracing, and least square method to reconstruct the 3D model of the soil specimen during triaxial testing. It was developed for unsaturated soils, but in fact, it can be used for both saturated and unsaturated soils. So the accuracy for the point measurement is less than 5 micron in the air and 76 micron in water. So this is the number is the number 200 safe. It is also the ability of human eye to see the difference, which means as long as you can see there is a small moments, we can measure it. The accuracy for the total volume measurements is less than 0.25%. And it's simple and cost effective. The major limitation of this method is it involves a lot of calculations and it's very computational intensive. But we have a software to do it for the one camera system. You just need 3 minutes for the load stuff. But now my student has improved it into 2 or 3 seconds per loading step. Okay, I think that concludes my presentation. Thank you very much for your attention. I can answer any questions if you have.
Thank you, Professor Zhang. It's a very good presentation, very impressive.
So I will stop sharing, right?
Yes. Does any of you have any questions? Just feel free to
Stop sharing.
type in the chat box or directly raise your hand and ask Dr. Zhang.
Yeah, I see a lot of my students here. So we have you and another student. So David, do you have any question?
Hello, everyone. David from South Africa here. Your presentation was very impressive. I have a question about the setup of the photogrammetry, the dots. How do you prepare it? The membrane is latex. I know that part.
Yeah.
Now, yes. So that setup of the dots is, so how do you print it and how do you make sure that it stays the same size in the sample? Yes, yes, here.
Okay, yeah. Printing a membrane requires a special type of ink. Okay.
Oh, okay.
Yeah. So that it can be quickly dry. Okay. So actually, we do not require the coated targets to remain the same shape. Actually, if you look at the picture, when we do the triaxial testing, even if it is a very standard circular shape, when you put it into the triaxial cell, it will
Yes,
become a ellipse, right? It
yes.
become elliptical shape. And yeah, I have a special program. Let me say, I have a special program which can allow me to find out its shape. If you look at it here, this is an elliptical shape, right?
Yes.
So yeah, we write a special program. I can slightly introduce a little bit
Oh, okay,
here.
okay.
So this is the design of the coded targets, right? So what you can do say is it's a circular shape. Okay. So what we will do is when you take a picture, if it becomes an elliptical shape, so what we will do is we will fit the elliptical shape with the standard ellipse, right?
Yes.
And then we will transform it back into a perfect cylindrical, round circular shape, right? And then, yeah, we can do the analysis. And then there's a notch. The notch is a starting point which we can use for numbering. And then if there's a protrusion, it could be 0. And if there's a blank, it be 1, right? So that you have 0, 1, for example, this is 1, 0, 1, 1, 1, 0, 1, 1, 1, and so forth. So this is a binary code. If you use the binary code, you can automatically give you a number, right? So this is the reason for each of them, we have an ID number for it. And then when we do the measurements, actually the outside just give the number. The inside, the solid points give you the location. So we did not use the solid points itself, its coordinates to as location of the points, because it involves about 200 to 300 pixel match patch. So we use the centroid of this point. As a result, it is a mathematical point. It has no physical size, right?
Yes.
So every time, in this way, every time we are picking up the same mathematical point. This is the reason why we can achieve an accuracy which is less than 1 pixel.
Oh, that's very smart.
Yeah, and then actually we do not need so many points, right? theoretically, we just need 2 points on the membrane, and the rest we can give them numbers, right? But we use the knot of the points as a redundancy. So yeah, we not only use the co-detectors, we also use the points between the co-detectors, right?
Yes.
In this way, we have much more, 3 times more points, which we do the measurements, which is equivalent. So every point there is equivalent to an LVDT, non-contact LVDT. So by
Yeah.
now, my student Xiang Xia can put about 3,000 points on the specimen, so that you have a very dense point cloud to represent the soil.
Yeah. All right. I understand now. Now it's very, very smart and intelligent. Thank you for that.
Yeah. Thank you very much for your interest and the question. Any other question from our own group? Okay. I saw Bishua is there. So are you still there?
Yes, I'm still here. Hi, Dr. Zhang. How are you?
How are you?
Yeah, I'm doing good. How are you doing?
Good, good. Do you have any question?
No, I already
No, I'm not.
we
Right?
discussed that before. Yeah.
Okay, okay,
Several. Yeah. Thank you very much for the presentation.
okay. So, Ahmad, do you have any question? Are you there? Okay. Do you have any question? I cannot hear you. Yeah. Anyway, you can type your, if you have question, you can type it.